Hi, my name is Bernie Kimbacher, and welcome to this behind the scenes of Hive VFX session. In the next half hour, we're going to go through the architecture of a global, fully scalable and cost-effective VFX studio in AWS. We'll be looking at multiple AWS services, and I will try to give a brief description of each, along with a practical demo and how I incorporated each service in the studio setup. I'm hoping this will make it interesting and accessible, whether you have prior knowledge of cloud workflows in general, or AWS in particular, or not. Before we begin, let me give you a quick intro of where I'm coming from and how Hive got created. I've been working in visual effects for the last 15 years and started to become interested in cloud workflows, especially for high-performance computing applications such as visual effects around 2015. I don't have any traditional education in IT or programming, but I've gained a good base of both with experience over the years. I think this entire webinar should be easy to follow whether you're coming from an IT background or an artist background, as long as you have some interest in the technical aspects of visual effects. With that being said, let me give you a few hard numbers on how Hive is operating. Hive has been in operation since May of 2019 and is fully AWS native since October of 2019. We're able to execute projects of any size up to and including triple-digit shot shows. In order to make the best possible use of talent and tax credits across the globe, we provision on-demand infrastructure in all supported AWS regions worldwide. The most common regions we use are US West 2, which is Oregon, serving the West Coast, CA Central 1, which is Montreal, serving the East Coast, EU Central 1, which is Frankfurt, serving all of Europe, and AP Southeast 2, which is Sydney, serving Australia. We can also enable cross-region data synchronization on a per-project basis, depending on where artists are located for each individual project. This way we don't have to synchronize all data to all regions, keeping our storage costs lower. Early on, I created a mission statement for Hive in order for me to stay on track for what I set out to create. First on that list was to rethink the traditional studio model from the ground up. This helps me to always be reminded to question everything we have come to accept as normal or standard in how we create visual effects and what our work environment looks like. Being a one-man show, the mandate was to create a well-functioning VFX studio that is able to execute projects both small and large with minimal upfront investment. The most important cultural pillar is to be able to provide a healthy work-life balance for both myself and all other freelance artists who work with Hive. This not only means trying to keep work hours reasonable, but also give everyone the freedom to work from where they are most comfortable at. For myself, this means being nestled within the Austrian Alps. Creating a decentralized studio setup of course also means not having to deal with expenses such as office rent, while also getting rid of physical infrastructure limitations. On the operations side, I knew I needed to stay as efficient as possible, meaning not having any resource idling. Cloud in general and AWS in particular give us some great tools to make sure we never have resources just sitting there and creating unnecessary cost. Finally, I wanted to have a studio that can scale from 0 to any size instantly, essentially creating a pop-up studio, very much the way production site setups work, which are created for a single project and then torn down after. At the moment, we can go from idle, meaning only having the essential studio data stored in S3 along with the bare serverless infrastructure, to a fully functioning studio within 10 minutes with the push of a button. We're going to make use of several AWS services during the session. There are more services involved in the background, but here are the main services we're using for each component. On the storage side, we're going to take a look at S3 and FSX for Lustre, which provide both extremely durable as well as high-performance storage. Our compute components will of course include EC2, which is where the workstation and compute nodes will be hosted, as well as Lambda, which is responsible for the management of resources, and Deadline as our render manager. There's also a small database component we need to store some infrastructure information. For that, we'll take a look at DynamoDB. Any AWS architecture needs to incorporate identity and access management. We won't go very deep into IAM, but it will be sprinkled throughout this demo. On the management side, we'll look at AWS Organizations, AWS Systems Manager, in particular the parameter store, and CloudFormation for our infrastructure deployments. For our network interface from the outside world, we'll see how Route 53 and Amazon API Gateway can help us provide users with on-demand access to resources. Before we finally get going, let me give you a quick overview of today's session. I broke it up into 6 sections. First, we're going to look at AWS Organizations and why setting up a multi-account environment can be beneficial. Following is a brief intro to CloudFormation with a simple demo deployment of a few IAM components, so we can understand the basic concepts of infrastructure as code and how this can help us manage a global deployment without the need for an entire IT department. After that, we'll look at the big topic of serverless architecture and how we can take advantage of it to build a scalable and cost-effective base for our VFX studio. We will explore setting up an API with Route 53 and API Gateway, which is backed by a Lambda function. Lambda in turn will use DynamoDB and the parameter store to keep track of the studio's infrastructure state. Everything else we'll look at after this will be based on these concepts to some extent. Of course, the Visual Effects Studio needs a very fast and highly durable storage. We'll look at how S3 and FSX for Lustre play together to achieve both of these, and in addition we'll explore cross-region replication, which enables global teams to collaborate, as well as automated deployment of our FSX file system in order to keep our operational costs at a minimum. Next we'll move on to virtual workstations. I'll have a demo on how to build a custom AMI from scratch based on CentOS 7, as well as how to provision individual workstations on demand via our Lambda-backed API. Finally, we'll look at how to set up deadlines so we can use Spot Fleets in order to be able to render at any scale while controlling costs. At the end of this demo, we'll see how we can have a global setup which at its idle state has minimum cost and can scale the full operation in any region within minutes. Okay, let's start with AWS Organizations and see how they can help us with creating our cloud-based studio. Generally, it's always a good idea to use multiple AWS accounts that are grouped within an AWS organization, as it gives you several advantages over operating out of just a single account. The structure is such that you create one root account, from which you can centrally manage all other accounts, which are themselves grouped under organizational units. In most cases, the root account only serves very few purposes, consolidated billing being the primary one. In my case, I also run a license server from this root account, which is shared among all other accounts. But you could, and maybe should, create a separate account for just that to follow AWS best practices. You can also set what's called an organization control policy from the root account. This allows you to restrict which services and regions are available to the child accounts, which helps with tightening security and also avoids overbilling by limiting what can be deployed in your organization accounts. Another great benefit is that you can separate different work environments. For example, you could set up organizational units for production, development, and testing, and create individual accounts within those units. Maybe you want to have a separate film and a separate TV account under your production OU, or even accounts for individual projects. This effectively creates air-gapped environments, which reduces the blast radius should something go wrong in one of your accounts. And one of the most important advantages with AWS Organizations in setting up a global studio is that it allows us to deploy CloudFormation templates across multiple accounts and regions from one central point. So instead of having to maintain individual regions by themselves, which could create significant IT overhead, we can change settings and update infrastructure from one central place and push it out to all other accounts and regions and know that every region is set up identically. Setting up an organization in AWS is super easy. From the management console, find the organization service and just follow the create organization link. And just like that, we have an AWS organization with one account in it. That's going to be our root account. If we want to add another account to our organization, we can just click the add account, then create account. We need to give our account a name and a unique email address. And we also need to create a role, which we'll use to access the account. I'll just keep the default role name. Click create. And if we refresh the page after a few seconds, we can see our new account is created. In order to switch to that account, we just need to copy the account ID, then go to our account menu and click switch role. Here we need to paste in the account ID and the role we just created in that account. We can give it a friendly display name and pick a color. And now we can see we are in our dev account. If we want to switch back to the root account, we can do that from the account menu as well. Moving on, let's take a look at CloudFormation now. This service is incredibly powerful in helping you manage and maintain your AWS environment. The concept is known as Infrastructure as Code, or IAC. Using CloudFormation enables you to version control your entire infrastructure. Think of the way you can version control, patch, update, and roll back your software applications and extend that to all of your infrastructure that you would usually think of as physical hardware. This way you can deploy complex infrastructure designs in a consistent and efficient manner. Doing the same task manually over multiple regions would be incredibly time-consuming and also prone to human error. And once deployed, you can easily manage your entire infrastructure, which may span multiple accounts and regions from one central point. Finally, CloudFormation also allows us to completely remove all infrastructure that was created by simply deleting the stack. Okay, let's see what this looks like in action. I'm in the management console for a demo account I created for this session. You can see I have several shortcuts to different services at the top of my page. This is a really handy way to quickly jump between services you access frequently, and you can simply add them by clicking on the pin icon and then drag and drop any service you want to add. So let's jump over to the CloudFormation service. If you don't have any active stacks in the region, you'll see the AWS welcome screen. Let's go ahead and create a stack. In the Create Stack wizard, you can choose to upload a template, use a sample template, but in our case, we're going to open up the template designer. The designer gives you a graphical representation of your CloudFormation template, which is handy when you're just getting started with the service. I already have a simple template copied to my clipboard, so I'm just going to open a template tab at the bottom, switch over to YAML and paste it in there. Once we have that, I can refresh the graphical interface at the top. So we can see the template contains a handful of components. We have a deadline spot plugin policy, which is linked to a group, and that group has a user connected to it called deadline spot plugin user. We also have a workstation role, which is connected to an instance profile, which we use to give EC2 instances specific permissions. Looking at the template code, we can see each of the individual components. I won't be able to go into detail on how templates are structured, but let's take a quick look at what each of these components look like. If we open up the workstation role, we can see an IAM role type resource. It has 3 AWS managed policies attached to it, as well as an inline policy giving it permission to put objects into a specific bucket. And we're allowing the EC2 service to assume that role. The workstation instance profile resource is very short. It simply has a name which we can use to assign it to EC2 instance, and it is referencing the workstation role. Looking at the user resource, it's also pretty short. It has 1 AWS managed policy attached to it, and it's also part of the Spot plugin group, which itself is also very short. All it has is a group name that's attached to it. Lastly, let's look at the policy that is attached to the group. We can see there's a lot more code in there, giving the Spot plugin group very specific access rights, and these are simply taken from the deadline documentation. So in order to create these resources, we can first validate the template to make sure there's no typos or anything like that, and then we can create the stack. The template is uploaded to S3, then we simply have to give the stack a name. I'll leave all the options as default, as this would go way beyond what we can cover in this session. Since we're creating IAM resources, we have to acknowledge that fact and then go ahead and create the stack. We'll see our resources created in a logical order according to their dependencies. I'm going to speed this up a bit until we see the stack has a create complete status. We can jump over to the IAM console and confirm that our resources are now created, and we can see our new user and also our new role we just created. If we want to delete all resources we just created, we can simply go ahead and delete the entire stack, and AWS will clean up everything. This way you won't end up with old unused resources in your environment, which could potentially pose security risks. Now let's look at what a more complex template can look like. Here's the template I'm using to deploy the basic serverless components of my Cloud Studio. You can see the resources section we've seen before, but these templates support a few more than just that. You can give your template a description, making it easier to collaborate with other people on your team. With parameters, you can customize your template and avoid having to hard code your template. Metadata is used to organize the way the parameters are presented, and conditions add some extra flexibility to your template. Mappings are useful for several things. I'm using it here to map out the CIDR ranges for my different regions. The resources section is fairly long, so I've grouped them together to organize the template better. We have some base VPC components, such as the VPC itself, subnets, internet gateways, etc. Then there are security groups defined for the different components of the studio. Several IAM components like we've seen in our demo template, just more of them. We're defining a shotgun API, as well as a scheduler function. And we also have a section which establishes a peering connection to the root account, so we have access to the license server. Finally, there's the output section, which is handy to give other templates access to components that are defined in this template. Okay, let's look at how to deploy this template to multiple regions using CloudFormation. I'm back in my root account management console. Let's jump over to CloudFormation. This time I'm going to go to stack sets and I'm going to create a new stack set. I'll upload the template file we just looked at and click next. We need to give our stack set a name, and below we can see the parameters from the template. The default values are fine for my development account, so I'll just click next. To keep things simple, I'll leave the permissions set to service managed permissions and click next again. Which brings us to the deployment options. I want to deploy this to an organizational unit, so I'll have to jump over to the organizations console and get the ID of the unit I want to deploy to, in this case, the development OU. I'll disable automatic deployments, which can deploy the template to accounts that are added after deployment, and I'll just pick 2 regions to deploy to, Frankfurt and Oregon. Next, to get to the review page, we'll have to acknowledge the fact that we're creating IAM components again, and then we can submit. And we can see the infrastructure is being created. I'll just pause this video until that's done. And we can see our deployment succeeded. Looking at the stack instances, we can see one in EU Central 1, which is Frankfurt, and one in US West 2, which is Oregon. And both stacks are of course current, since we just deployed it. If we jump over to the sandbox account we deployed this to, and go to stacks, we can see the newly created stack, along with all the resources created by the template. Let's move on to the concept of serverless architecture. First, I want to give you a high-level overview of how an artist interacts with AWS via Route 53 and API Gateway. An artist never has to directly interact with any AWS service. Rather, they log into their familiar Shotgun environment. This could of course be integrated with any other software from which you can call an API. I just happen to use Shotgun. From there, the artist can make secure API calls via Shotgun's action menu items, such as starting or rebooting the cloud workstation. Route 53 chooses the best region based on latency. So for artists located in Vancouver, for example, the API call would be forwarded to the US West 2 region. Let's take a quick look at what this looks like in the AWS console. Here I am in a management console for my Hive production account. Let's jump over to Route 53. We can see we have one hosted zone. If we take a look inside this hosted zone, we can see several records. I blurred most of them out for security reasons, but you can see the 3 records starting with API. Again, I blurred out the rest of the domain, but they all point to the exact same domain. We can see these records use a latency-based routing policy, each of them pointing to a different region, and traffic is routed to the API, which we'll look at next. So back at the management console, let's jump over to the API Gateway service. Here we have one API that was created with our CloudFormation template called Shotgun API. If we open it up and take a look at the integration tab, we can see a default route which is backed by a Lambda function, and it's pointing to our Lambda function which, like everything else, was also created by our CloudFormation template. So all API calls are forwarded and processed by the serverless Lambda function, meaning the API is always ready to receive calls, but there's no ongoing cost associated for having a multi-region API. So now that we have looked at how API calls are directed to the correct region, let's take a look at how things work inside a region. In an idle state, there are 3 main components. The API gateway with the Lambda functions, which handle the API calls, and we also have a scheduler function, which runs in certain intervals. Then there's the DynamoDB component, which is used to store information about the state of the region's infrastructure. And finally, a S3 bucket holding all the long-lived data. So when a region is idle, there are only serverless components, meaning there's no ongoing cost aside from the S3 storage costs. All other resources are created either on demand via API call or on a set schedule via the scheduler function. Let's take a quick look at these components in the management console. Starting with the Lambda functions, we see all these functions created by our CloudFormation template. At the top we see the API function and below the scheduler function, all running Python code. If we go into the scheduler function, we see the function code at the bottom, but going into that will go well beyond the time frame for this session, and we also see the event bridge, which triggers the schedule at a rate of 5 minutes in this case. Next we can look at the DynamoDB component, and under tables we can see the Hive resource tracker that was created. Looking at the items, we only see a couple of entries since this region is currently in an idle state. This is a rough overview of the serverless architecture that is orchestrating all other resources within the studio environment. At the end of the session, we'll have a quick look at what this looks like from an artist's perspective. Okay, let's move on to storage. Here's a high-level overview of the storage setup within a region. We have an S3 bucket which holds all of our long-term data. The main benefits of S3 are the extreme durability of the famous 11 nines and the low cost of storage. So it's perfect for our needs. This S3 storage serves as a data repository for the FSX file system. FSX is a POSIX-compliant file system with a scalable throughput depending on the size of the file system. You can get up to 200 megabytes per second per terabyte of sustained throughput with burst throughputs in the gigabytes. This, coupled with the low latency access times, makes it a great choice for graphics workstations. These workstations have another very useful storage tier, aside from their root device, and that is a locally mounted NVMe drive, which are great for application caches. Looking at the data flow from a multi-region perspective, we're making use of the cross-region replication feature of S3 to push data between regions. In each region, new data arriving in S3 is automatically being fed into the FSX file system. When an artist creates and publishes in a region, that data is being pushed back to S3 immediately and then again replicated to the other regions. This cross-region replication is configured on a per-project basis, so it's easy to configure which region holds what data, and it avoids that all data is in all regions, which keeps storage costs lower. Let's have a quick look at how this is implemented in the console again. I'm going to jump over to the CloudFormation console again, and under stack sets, next to the VPC stacks that we already looked at, we have a FSX stack set as well. This is also centrally deployed to all our production regions, in this case CS Central 1, EU Central 1 and US West 2. If we take a look at the parameters, we have a backup interval which can be set with a rate expression, our deployment type, and further down we have a start time, which is a cron expression specifying when the FSX should be started, in this case from Monday to Friday at 0600 UTC. If this is left blank, the FSX will only start on demand. We'll see that at the end of the session. Moving along, let's look at building a custom workstation AMI from scratch. I'm back in the management console of my demo account. Let's jump over to the EC2 console. From here, we can simply click the Launch Instance button. First, we'll need to pick a base AMI to start from. Let's just type CentOS in the search field and see what's available in the marketplace. And here's the CentOS 7 image we're looking for at the top of the list. Let's select that. Next, we need to choose an instance type. So let's filter by GPU instances, and we want to use the latest generation G4 instance types. I'll go with a 4 extra large. On the next page, the only thing we'll have to set is the IAM role, so we have access to S3. In this case, I don't have an instance profile set up, so I'll just go ahead and create a new IAM role. Just click Create Role, pick the service you want to grant access, in our case EC2, and go to Permissions. We'll just pick an AWS Managed Policy, which provides read access to S3. Go next to Tags, and next again to Review. Here we have to give our new role a name, and click Create. We can see a new role in the list, so let's close our IAM tab and go back to EC2. We just need to refresh the dropdown, and we'll have our new role available. With that said, we can go to the storage page. By default, this image gets 8 GB of storage. In our case, we'll need a bit more than that. Let's go with 25. I'll also want to delete the volume when we terminate the instance, and encryption is always a good idea. You can tag your instance to make it easy to track your resources, but I'll leave it empty and go to security groups. I'll just change the name and also set the source to my IP instead of having it wide open. With that, we can go ahead and launch. We'll have to pick a key pair to get SSH access. In my case, I'll just create a new key pair to use and download that to my local drive. And with that, our instance is booting up. Once our instance is up and running, we can go ahead and connect to it. The connect button opens a little instructions page for us. First, we have to change the permission on the key file we just downloaded. I'll just copy that and switch to terminal, find my key and paste in the chmod command. Now we can copy the public DNS name of our instance, head back to the terminal and SSH in using our key pair. We have to confirm the fingerprint and we're connected. First thing is to set the password for the default CentOS user, and then we can run a full system update. I'll be speeding up all the install processes in this video. With the update done, it's a good idea to reboot since most likely there was a kernel update. We'll SSH in again and run another update to make sure we are in fact all up to date, and looks like we are. For the installation we'll need the wget package, so let's install that too. Let's first install the FSX drivers so we can mount our file system. Like with any AWS documentation, you can easily find it by googling AWS followed by the specific component you're interested in. It's usually within the first 2 hits. We'll just find our operating system and hear all the instructions, so let's go ahead and run these on our instance. Next we'll need to install the EPEL repository, and I'll also install the Nano text editor. And now we can install a desktop environment. I'll install a default GNOME environment. We'll also need a few extra packages. Depending on what software you're planning on running, you might have to install extra ones. Now we can set our graphical interface to start by default and also disable the OS level firewall since we'll use security groups to manage that. Next, we'll install the NVIDIA driver. Again, a quick Google will get you to the AWS documentation. We'll want the grid drivers for G3 and G4 instances, and here are the instructions we're looking for. Let's install that. First, we need to update a couple of files and rebuild the grub config. I'll also make a mount folder called data and reboot again. Give it a minute and then we can SSH in again. We need the AWS CLI to access S3, so let's install that. Now we can download the NVIDIA driver. We need to stop the GDM service, then we can go ahead and run the installer. we can remove the install file and make sure the driver is working. Then we can set some properties as per the documentation. Finally, we can install a TerraDG agent. These instructions can be found on the website. Of course, if you want to use a different software, you can skip this. You would also have to enter the TerraDG code, but in my case this is automatically done when the workstations are provisioned, so I'll just exit out of here and head back to the console and stop the instance. Once stopped, we can just right click and go Image, Create Image. Give it a name and a description and click Create Image. And here we have our custom AMI being built. Now that we have a workstation AMI, let's take a look at how an artist workstation is provisioned on demand. As a refresher, let's look at what is going on in the background. As an artist makes an API call from Shotgun, that is forwarded to the artist's closest region. In the region, the API call is handled by a Lambda function, which will provision an FSX file system if there isn't already one active. And once we have an active file system, it will provision the artist's workstation. Let's take a look at this in action. Here I'm in my Shotgun tasks page. An artist can simply right-click on any Shotgun asset and from there manage their workstation. We have the option to start or stop a workstation, reboot it in case it freezes up, and we can also change the IP ingress to the workstation since a lot of people are connecting from home and they won't have a static IP assigned. If we go to Start Workstation, the API will figure out the current state of the region and then provision infrastructure accordingly. In this case, there was no active FSX file system, so we get the message that one is now being created, and that takes about 10 minutes. As mentioned earlier, we can avoid this wait time by specifying a start time for the FSX. For example, we could set it so that at 8 AM every morning, the FSX is starting up, and by the time artists log in, it will be ready to go. Let's take a quick look at the management console again. I'll jump over to CloudFormation, and here we can see the FSX auto stack is being created. If we look at the resources, we can see the FSX file system is being created, and we can also see it by going to the FSX console. Now that we have waited 10 minutes, let's see what happens if we try to start our workstation again. Let's go to Start My Workstation again, and this time we see a success message saying that the instance for Bernie K, that is my user, is starting up in EU Central 1. We also get a login URL, which I've blurred out again. If we jump over to our EC2 console, we can see that the workstation is starting up, and also the Deadline server was started. After a couple of minutes, we can go to the TerraDG client, connect to the workstation, enter a password, and we're connected to our cloud workstation. This brings us to the last part of our session, how to set up Deadline to take advantage of AWS Spot Fleets. I'm in the EC2 console of my production account here, and you can see I have a render node image next to my workstation image. Creating this image is similar to creating the workstation image, just with fewer components. For example, you don't need a graphical user interface or a TerraDG client on these. In order to use this AMI with Deadline, we need to create a config file that we will then use in the Deadline settings. In order to get that, let's head over to Spot Requests and create a new Spot request. We need to select our render node AMI. Then we need to pick an instance type. This will depend on the kind of rendering you're doing. I'll just pick a 32 GB compute optimized instance type. We also need to select the VPC that was created by our CloudFormation template, and I'll select all 3 subnets we created. We can pick a maximum capacity for our render nodes. I'll just use 100 for this demo, and it's important that you check the Maintain Target Capacity checkbox. Next, I'll uncheck the Apply Recommendations checkbox and pick some instance types myself. I'll just go with all the C5 for extra large instance types. This will give us enough instance pools to get a strong fleet. And now, instead of launching this, I want to download the JSON config file. We can open this in the code editor and we can see the Spot config we just created. In order for Deadline to use this, we just need to make one small adjustment. I'll select all the text and add an extra indent. Then at the top, I'll add a curly bracket and specify a group name. When a render job is submitted to Deadline which matches this group name, Deadline will launch the appropriate number of Spot instances for the render job. Note that you can use wildcards here, so in my case any group that starts with spot underscore will be matched. Now I'll just need to add the corresponding curly bracket at the end and copy the entire text. Next we need to open a Deadline monitor on a workstation and go to Configure Events and then choose Spot. We need to enable a service, set the correct region and then paste in the config we just copied to our clipboard. We can also specify an idle shutdown parameter. This is the number of minutes a Spot instance has to be idle before Deadline shuts it back down. Finally, we have to paste in the IAM credentials. In my case, that was created by the CloudFormation template, so I'll just paste that in here. And that's all there is to it to enable Spot Fleet rendering in Deadline. Now you can access unused AWS compute capacity at a fraction of the on-demand price. Okay, that's all we have time for today. I hope you enjoyed the session and got some good information from it. If you're considering cloud workflows or if you're just interested in general, I encourage you to just start playing around. And if you have any questions or need help finding solutions for your studio, feel free to send me an email at bernie@hivevfx.com. Thanks for watching and stay safe.